It's dark.
I'm sorry?
So here is dark already, it's night. Yeah. We changed,
Yeah.
the time last weekend and
Uh-huh.
now we are, yeah. So it's the fall now.
Yeah.
Yeah.
Yeah. Yeah, nice. So if you don't mind, can we start? Because I have tendency to start on time.
Yeah, no
Yeah,
problem. I'm here.
okay. Yeah, okay. So welcome back, everyone, for this new academic year. And today it's our pleasure to have Professor Zuazua, who will be talking about the interface of machine learning, control theory, and PDEs. Yeah, thank you. So you hear me? You can start. Yeah.
Yeah. Should I start?
Yeah. So
Okay. Thank you. Thank you then. Thank you for the kind invitation. So I'm here to present our recent work in the context of the interface between machine learning and control, also with some relevant PDE ingredients. So this time it will be more PDEs for machine learning than all the way around, where you will find, of course, many more works related to the development of the new methodologies of computational mathematics employed or based on machine learning and neural network ansatz. So here I will take the other perspective, how we can employ some of the existing tools in partial differential equations, which are somehow classical to some extent, in order to better understand algorithms in machine learning. Of course, the context you all know. Now it seems that machine learning is everywhere in our daily life, but also in the big science, trying to contribute to solve these challenges that until now were not reachable. Some people claim, well, this is a bubble. Some others believe that this is a new revolution that will stay, that will transform our lives and the way we do, in particular, mathematics and science. But, well, this is not the topic of the discussion. Just I open the question. You can think on that yourself and make your own analysis. Somehow mine will be implicit in the presentation I will do. Okay? So let me begin by a classical control problem. This is a herding problem. I'm not sure you can hear the video, but you can see it. So this is a herding problem. This is a competition of shepherd dogs in the Basque Country near Bilbao, where I am born. And what you see is how the shepherd is guiding the dog, the shepherd dog, that has to, with his motion, has to push this flock of sheep to go through the gate that you can see behind up, right? So you can see it up there. The video is a bit slow, but I hope you can see it. So this is a competition of shepherd dogs, right? So the competition is not among shepherds, it's among shepherd dogs. So the dog has to be trained in a way that the shepherd can control its instinct. And as you see, most of the time, the shepherd is telling the dog, gel the or, meaning stop, stop. Because otherwise, the intuition of the dog is to rapidly, run after sheep. But if he will do that, then sheep will disperse. And once they disperse, the game is lost because it will take a long time until the dog is able to gather them again if he can do it. Of course, the competition is won by the shepherd and the dog, who are able to drive the flock of sheep to the gate basically in a minimal time, okay? So then what you see that the shepherd is asking the dog to stay quiet. The dog, his intuition is always to do some zigzag dance, because he knows that whenever the dog moves to the left, sheep, in order to avoid the proximity of the dog, will do the opposite, will move to the right, and vice versa, right? So, but then most of the time, the dog has to stay quiet because sheep have the tendency to simply be together and continue their path. So the dog is there just like an impulsional control, being active just a few times, and for the rest of the time being in an off situation. So this is a typical case where you see a control will be of the form +1, 0, -1, 0, +1, 0, -1, 0, but most of the time is 0. Is the time where the shepherd is telling the dog, Geldior, Geldior, be quiet, just let, sheep to evolve spontaneously all together according to, the inertia they developed. Okay, so this is a classical control problem for animal behavior. Um, I think my screen is frozen. Let me open it again. So maybe I should just open the screen in my computer. It will be better, probably. I think we are losing quality by transferring the screen from the tablet. Okay, so this was a control application to. So can you see the screen now?
Yeah, we can see it, yes.
Okay, thank you. Thank you. Okay, I think it will be better now. Okay, so a few years ago, we were analyzing this problem. We wrote a couple of papers. I'm not sure I wrote the references here. So we wrote a couple of papers. The first one with Ramon Escobedo and Aichiber Ibañez first, I think 2016, for this problem in which one dog was controlling a flock of sheep. And then later with Dogman Co., I think it was during COVID, around 2020, we wrote a paper in which we were developing a model and a control strategy to do this, even in the presence of several dogs. So you have seen probably videos of giant flock of sheep in New Zealand, right? Thousands of sheep, where of course then as a dog and one single shepherd and one single dog is not able to regulate the dynamics of this giant flock, and they need to coordinate the action of the several dogs, right? So this is a simulation we did by writing the model, the one I have shown you. This is a Newtonian model, one dynamics for each of the sheep, one dynamics for each of the dog. This dynamics in interaction is asymmetric because, as I have explained, sheep with sheep, they like to be together. Sheep are afraid from the proximity of the dog, so they have the tendency to escape the dog. And on the contrary, dog like to be close to the sheep. And when you see, it took us some time to understand how to do this simulation. This simulation is exhibiting through, of course, computational control, how four dogs that in principle at rest, they are placed in this, say, polar configuration. Sheep are here in the middle, and the dog have instructions to bring this flock of sheep that is full of sheep. So you have here hundreds of sheep within this pave, to bring this sheep to the corresponding gate, which is placed here northeast. Okay, and then when you see what the dogs do, they develop this kind of dancing strategy that we can interpret a posteriori. A posteriori, we see that these complicated blue strategies that the dog are developing are building some kind of virtual diagonal corridor along which sheep are evolving spontaneously simply because, sheep are afraid of the proximity of the dogs. And therefore, what sheep try to do is at any time instance, they try to maximize the distance to the four dogs. So basically, these four dogs are defining a polygon that is evolving on time, and sheep instinctively have the tendency to place themselves, all together at the center of this polygon. While the polygon moves like an elevator, then sheep will move with it. Okay? So this is a classical application of control theory, classical control theory, developed for, in particular during the Industrial Revolution to deal with the classical challenges of, automotion, aeronautics, locomotion, transport, energy, all kind of industrial applications, regulation of all processes, chemical industry, energy, uh, natural resources, water, and so on. And then, as you know, this topic was very much developed in the 50s. In particular, at that time, we had the contributions of Kalman, of Pontryagin, of Richard Bellman. It was in this context of controlling finite dimensional systems where Richard Bellman, through the principle of dynamic programming, coined this concept of the course of dimensionality that nowadays became so popular through the classical problems, the typical problems in machine learning and artificial intelligence. Because what basically Richard Bellman said, well, you see, this problem that Enrique is telling you here shouldn't be that difficult. After all, it's just a matter of finding the geodesics. Yes, but it's finding the geodesics, is finding the optimal strategy for the motions of the dog in a huge space of a very high dimension. And therefore, when you try to explore all the possibilities, you simply fail. This is something we don't have any intuition about. Of course, as mathematicians, we can write a dynamical system of this form. We can write a control problem. We can write a cost function, prove maybe using the tools from the calculus of variation that there is an optimal control. We can always characterize this control through the Pontryagin maximum principle or the corresponding dynamic programming principle using Hamilton-Jacobi equations. But if you ask me what is the solution of that problem, what is the optimal solution, then I really don't know. So the only thing we can do is to apply a gradient descent strategy, and this is what we did in this context. And actually, the problem being huge in dimension, what we did was to apply a random batch method, a kind of a stochastic gradient descent algorithm, in order to reduce the computational cost, together with a model predictive control strategy, which, as you know, was also coined in order to deal with the possible errors in modeling when matching the true control dynamics. Okay, so this is classical control theory brought to a point where you start to face the challenges of the course of dimensionality, but you can still handle it by combining analytical understanding plus computational, say, skills. Okay, very good. Now, there is a good explanation of why all this is possible, and is due to several, individuals. I mentioned some of them already. So one of them is Norbert Wiener, who back in 1948, he defined the field of cybernetics as being the science of control and communication in animals and machines. This could be very much also the definition of modern artificial intelligence nowadays. At that time, he was more thinking maybe on classical robotics. They were not really thinking on a large language model that we could wear in our pockets to do all the kind of tasks we develop nowadays, as for instance, even doing research, exploration on on the possible links between different topics in applied mathematics and artificial intelligence, right? So that was Norbert Wiener, 48. And then in 58, there was this contribution by Kalman, who said, listen, even if you have a very huge dimensional dynamical system, it can be a social network with millions of individuals interlink, right? Through the dynamics given by the matrix A over there, and you have only a few controllers, you can still control this system under the condition that the matrices A driving the free dynamics and the matrix B representing how the controls are acting on the system fulfill this well-known Kalman rank condition, which says that the rank of B, AB up to AD minus 1B, D being the dimension of the system, is full, right? So this rank condition, this algebraic rank condition, is telling you whether this system is controllable or not. When the system is controllable, it means you can drive the system from any initial configuration to any final configuration. And whenever the rank is not full, is for instance, instead of being D is D minus 1, it means that you are missing some directions. Like for instance, we humans do, we are controllable on the plane, but we are not controllable on the space. Because we cannot fly, right? If we are embedded in the three-dimensional space, then our rank will be 2, will never be 3, okay? So you see that in 58, 10 years after the pioneering book on cybernetics by Wiener, was one fundamental contribution of Kalman, later developed in the nonlinear context, employing Lie brackets and so on, which very much explains what you have seen in the video: 4 dogs being able to control a flock of hundreds of sheep, right? So you see that from a mathematical perspective, we could say, well, the problem is solved. In practice, this is not really the case, because if the dimension of the system is very large, so D is, for instance, I don't know, 84 million Germans, so you have a system with 84 million components, certainly you don't want to compute the rank of this matrix. That would be simply impossible. And actually, one of the recent breakthroughs of DeepMind recently has been to develop new algorithms for multiplying matrices. So you see how, there is a classical link. This is very much, reflected in the very definition of Norbert Wiener. There is a classical link between control theory and artificial intelligence. Actually, artificial intelligence is very much like what we have been doing in control theory, but now moving into the context of data, right? But even nowadays, this feedback is being exploited in order to help computers to check conditions of controllability, which might be simply out of reach for classical computational methodologies. And this works, right? So you see, for instance, a classical application for parking a car, something that we theoretically know how to do, but which can be hard to do when, the space is narrow and there are many obstacles. So here you see a control that has been programmed in order to solve the Pontryagin system and is able to park the car optimally, right? We know that theoretically the optimal trajectory is something that is close to what we have observed in the video, but in practice we also know that this is very hard to achieve, in particular without getting your car collisioning the columns and scratching it. Okay, very good. So now, what is the relation of this classical control theory with machine learning? Well, this video of supervised learning, I think, explains very much what is the spirit of what we aim to do. There are no ships, there are data of 3 different colors, 3 different labels. And the first problem we try to solve is, well, can I build a neural network able to classify this data according to the labels or to the colors, so that data of different colors go to different destinations, right? So very much like when you try to split in a big photo folder cats and dogs, right? And you see this works, and again it looks like a system of particles, very much like the one we were dealing with for dogs and sheep, except that this time there are no dogs, right? So in this case, there seem to be ships of 3 different colors, and they seem to spontaneously evolve to the corresponding gates, without the actions of any dogs. Well, actually, when we started working on this topic, we realized that, well, this is not completely true. There are plenty of dogs there. The dogs here are the parameters of the neural network that have been trained so that the neural network is able to realize this classification property, successfully, except that, normally in machine learning, we don't consider these parameters as being controls. And of course, we never draw the dynamics of these parameters. Otherwise, you will see plenty of parameters oscillating. All the parameters of this neural network will be oscillating in order to be able to realize this property of classification, which is, of course, very much also the property of representation of the data set, the first step in order to be able later to generalize and to extrapolate, right? So once you see this link, you start to wonder what are the analytical foundations of this field of machine learning, why is actually nowadays working so well. And you see again some of the names we already mentioned. So the first theorem of universal approximation is actually due to Norbert Wiener back in 32 in his celebrated papers on Tauberian theorems, 100 pages at that time. At that time, this was a paper on Fourier analysis, right? That was the golden age of Fourier analysis, Palais, Wiener, and so on. And then he said the following: give me a Gaussian like G here, right? The one drawn here as basis function. If you let me translate this Gaussian multiplied by weights and combine them, then I can generate a dense class of functions. So at that time, for Wiener, that was a natural statement. His proof is actually not very difficult. The only thing you need is that the basis function G taken here to have a Fourier transform that never vanishes, something that of course is true for the Gaussian, because the Fourier transform of the Gaussian is the Gaussian and it never vanishes. And with this result, he was inaugurating the age of nonlinear approximation theory. Why? Because contrary to the classical theorems of density, namely polynomial density, Stone-Weierstrass, density of Fourier series, density of finite elements, and so on. In this case, the basis functions move according to the parameters B. So the centers of gravity in this approximation B can be chosen arbitrarily. This is why this is a nonlinear approximation ansatz. Why? Because although the ansatz depends linearly on W, as in classical linear approximation theory, it depends nonlinearly on B, right? So at that time, Norbert Wiener started, inaugurated this era of nonlinear approximation theory. At that time, he didn't know that. He didn't know that this theorem will be called later the theorem of universal approximation, and that will be one of the foundational columns, basements of modern machine learning. It took 57 years until Sivenko was able to generalize this theorem to cope with to modify the Gaussian to become a sigmoid. People were very happy when Sivenko was able to do this, because this sigmoid is really, reflecting the off-on, activity of a human brain neuron. And for doing that, of course, Sivenko, the main observation of Sivenko was, I need one parameter more than Wiener. I need in particular to be allowed to scale the variable x, because, of course, Wiener theorem doesn't apply, because the Fourier transform of the sigmoid doesn't fulfill the condition that the Fourier transform doesn't vanish anywhere. It's more like a sinc oscillatory function, okay? So this was when people realized, oh, this is really getting close to human neurons, because there is this off-on, either active, non-active of each of the neurons in this ansatz. If we determine that each of the nodes or each of the terms in this series where I am piling up the different terms is considered to be as a neuron that can be either off or on, depending on whether I am to the left or to the right, because of the choice of the parameters. And nowadays, as you know, we often choose to use, instead of taking the sigmoid, to take the ReLU function, which is essentially the simplest function that reproduces this behavior of being off to the left, being active to the right, being also globally elliptic, something that is nice in order to have stability properties. Okay, so that was the start perspective of interpretability. It was very hard to manipulate, this kind of density results by Sivenko or by Wiener, because I'm piling up just instantaneously all neurons one after the other. And for us, it's very hard to understand how this density approximation is realized. People realized that it was easier to, increase our understanding and interpretability of what neural networks were doing if we will move into a deep, say, setting where we are accumulating neurons step by step, very much like in a time discrete dynamical system. And it is in this way that you see how dynamical systems theory emerges, and the very close link with control theory arises very naturally when you say, well, instead of doing like Sivenko or Wiener, I add neurons one by one in a time discrete setting. Then I get a time discrete dynamical system, which is very much the Euler discretization of the differential equation down here, right? Which is a nice differential equation because the nonlinearity is the sigma, the ReLU, for instance, which is global elliptic. So this ordinary differential equation is well posed, and the coefficients W, A, and B, the scaling A, the drift B, and also the amplitude W become now time dependent, very much as in a classical control problem, except that now the control problem is nonlinear because of the presence of the sigma sigmoid or ReLU activation function. So one big difference in machine learning, although this can be understood as a control problem, a very important difference of classical machine learning with control theory is that in control theory, we build a control in order to bring one rocket from Earth to the moon, right? While in machine learning, we want the same controls to be able to handle all data simultaneously and classify them according to the corresponding labels. So we are dealing with giant simultaneous or ensemble control problems. But, this can be done. We have seen it done in our video previously. And in fact, the proof that this can be done was published in collaboration with our former PhD student, Domènec Ruiz-Ballet, in Siam Review a couple of years ago, where we proved, yes, this can be done. Complicated is harder to write than to understand, right? And it's an induction proof, and it's also very much related to the classical results in optimal transport, in which you move data from one configuration to the other, given that, of course, the solutions of the ordinary differential equation can also be understood as the characteristics of the corresponding transport equation. So the reason why this very canonical model, and you see that here, this time, what we are doing is something that is extremely, very much the opposite to classical mechanics, right? Because in classical mechanics, we need to modify the ODE or the PDE in order to adapt it to each specific application. It's not the same ODE for a fluid, for elasticity, for a pendulum, for a car, or for an airplane, right? So dynamics under consideration. Here, the ODE is always the same. Regardless what the application is, we always consider the same ODE. And what we claim is that if the goal is to track data you can get, I don't know, in biomedical applications, in meteorology, or in the stock market, it doesn't really matter what the source this model, simply because you can match initial data to targets simultaneously, very much as we do in a Rubik cube, in which we can, put order by bringing every micro phase are homogeneous in color, right? And we bring this comparison to the Rubik cube because the proof of the controllability of the simultaneous controllability of this neural differential equation very much follows the principle of the Rubik cube, in which in every step we freeze part of the cube while the other one rotates, very much as we are going to do in here. Why? Because let's see what this ODE does. So assume we are managing this data. Maybe they are living in a very high dimensional space. So for instance, I am dealing with the data, the photo folder in my computer. The photos are colorful. So, they have plenty of pixels. The photos live, they can be embedded in a Euclidean space of a very high dimension. And this is the space in which this ordinary differential equation, this neural differential equation, is evolving, and is taking every photo and bringing it to the corresponding folder according to the person that I have allocated to each, of the folders. Okay, brother goes to brother, father goes to father, mom goes to mom, and so on. Okay, so why this ODE is able to solve this giant classification problem? Giant because the space dimension is huge, because the objects I'm dealing with are very complex. They are, photos or videos of high resolution, and because there are very many of them. So why this ODE is able to do that? Well, it's very easy to understand. When you look to what this dynamical system is doing, you see that there are 1, 2, 3 parameters. Sigma is always the same naive one-dimensional function, ReLU, 0 or linear. So A dot x plus b is a number. X is a vector representing the position of this item in this high-dimensional Euclidean space. A is another vector, is a vector of controls, multiplying scalarly x, and b is a number. So what is, sigma doing? Sigma is either 0 or active, depending on whether a dot x plus b is negative or positive. But what does it mean, a dot x plus b being negative or positive? It means simply that I am either on one side or to the other of the hyperplane of equation a dot x plus b equals 0. So what I'm doing with the right hand, I'm manipulating the controls A, B, I'm carrying a space into two halves according to the values of A and B, and then I am determining which is the active part, and the active part I'm pushing it with the other hand in the direction of the wind W the way I like. And in this way, I can solve the simultaneous control problem by an induction principle, very much as shown in this video, where we realize that out of 9 data, 8 of them are well classified. The blue, 2 blue are in the blue, the 3 green are in the green area, and the 3 red in the red area, but there is one that is badly classified. I have to bring the blue to the blue area, and in order to do that, I have to make sure that the others remain in the blue area. How can I do it? Well, I can't just do it using this idea of cutting and pushing and concatenating 4 different actions, very much like in a Rubik cube, right? So, and then you can see how it works. First action, left frozen, right goes up. Second action, up, down frozen, up goes left. Third action, up frozen, down goes left. And final action, left frozen, right goes up. So this is the reason why this can be done, and by induction, it can be brought to any dimension to, so you see, very much like in control theory, as I said in the beginning, in machine learning, we can discuss the mathematical principles of why it works. And I have shown you 2 of them. One of them is the density, the fact that I can achieve everything through functions that can be written as neural networks. It's just a matter of finding the corresponding coefficients, and control theory, which explains you how you can show that these coefficients exist. But in practical applications, when you have to solve this problem, very much like in classical control theory, you will not be able to compute the controls analytically. You will have to rely on the computer. And in order to do that, you will have to choose the architecture, take your data set, build a corresponding loss function, and then minimize this loss function in a huge dimensional space by employing a gradient descent or an stochastic gradient descent algorithm. So you see that somehow the ancestor of what we are doing nowadays in supervised learning is the classical least square principle of Gauss and Legendre, which is now 220 years old, right? We could say that Gauss and Legendre were the ones who pushed mathematics into this new direction of data representation, inaugurating, the age of machine learning by introducing this very basic idea of least squares that we continue nowadays, except that nowadays with the modern computers, we can deal with functions represented through huge neural networks and not simply linear or quadratic functions as they were doing it. Okay? Nowadays, as is explained in this beautiful web of 3 blue and brown, when you look to, for instance, the ChatGPT 3, not the 4, neither the 5th one, in ChatGPT 3, you have already 175 billion parameters. So we are optimizing the neural network in a space of 175 billion parameters, which is 20 more times the population of humans on Earth. Okay, so yeah, as mathematicians, we could say, oh, but you still are in a Euclidean space, and therefore by the calculus of variation, there will be a minimizer. Yes, but this is something you don't really want to solve by hand, right? Because every step in a gradient descent iteration will mean compute a gradient, and a gradient means 107, yeah?
Yeah.
175 billion partial derivatives. So this is the course of dimensionality. And furthermore, we are facing here the devil of non-convexity, because although the problem looks, nicely convex, it is not, due to the fact that each neuron is activated or unactivated through the ReLU function. So, of course, there has been a huge number of very smart contributions developed by the community in machine learning to bring the topic to the level of success of nowadays. One of the very beautiful ones is, for instance, this idea of the next token prediction, where people realize, well, actually, whenever you give me a text is not just a union of inputs, but there are even plenty of outputs, plenty of labels on it. You just need to associate to any sequence of words the next word. So out of this text, you can build the inputs and you can build the outputs, and you can, even a single page of text can be used in order to build a model that is able to manipulate and learn out of text through this principle of least squares or supervised learning. Of course, if you try to bring these very elementary architectures to the level of success of nowadays large language models, this will never be sufficient. For instance, this principle I have shown you of dealing with one datum per iteration, this will indicate that, well, you will need neural networks that are much bigger than the ones that are actually being used nowadays. Something that made the success and the revolution of modern large language models possible was this very remark in that celebrated paper back in 2017, Attention is All You Need, in which people realized, listen, if you combine this idea of, neural networks iterating in order to classify and represent data, if you iterate and you alternate, you interlace them with an idea in which data are compressed, then you will very much accelerate the classification process, simply because very much as the dog does in order to herd sheep, we could do here very much the same by just observing that instead of having here one single blue to classify, if I have had this blue surrounded by many other micro blues all around, clustered around the same blue, then all of them could have been brought together to the destination. This is something that we have a very good intuition of, right? It's very much intrinsic to the ideas of optimal transport, cluster, pack things to transport them and not doing it one by one. This is why when we move from one apartment to the other, we pack things into boxes and then we transport boxes. We just don't do item per item. So the same here, and this is something that can be done through the attention mechanism. And in particular, in this paper recently published with Albert Alcalde and Giovanni Fantucci in our team, we show that this attention mechanism can also be understood as a very rather simple dynamical systems in which the different items are particles interacting according to their geometrical position in the Euclidean space. And when you take into consideration the mutual forces, naturally you see that a number of leaders emerge, and these leaders have the tendency to absorb the data so that data are packed, and therefore the complexity of the neural networks you need can be diminished. And that means that whenever you are able to diminish the complexity of the neural networks, you can learn more and more data, and therefore you can build architectures that are smarter and smarter in order to respond to new prompts or to generalize to new scenarios, right? So finally, this is the kind of architecture that you will encounter in the transformers, in which you interlace, right, feed-forward layers of neural networks together with attention to compress, and then feed-forward layers to classify. And by letting the computer optimize the parameters in all these interlaced layers is when you are able to generate these transformers that enhance significantly the capacity of recording huge data sets. Okay, very good. So, but until now I was talking about control, classical control, a natural bridge from control to supervised learning. In supervised learning, we are representing data, we are classifying data. This is interesting. This is something we use a lot. For instance, as I said, in the photo folder of our computer, in order to put order automatically, the computer does it. You don't need to order one by one all the photos in the photo folder. It is sufficient that you put a label to every individual or some of the key individuals appearing in your pictures. And then you say to the photo folder, to the app, you say classify, and then you will see that it does it quite well. Of course, this photo ordering app will not do it perfectly. You will, for instance, experience that if you open the photo of your brother, for instance, in my case, I open the photo folder of my brother and I see, oh, the computer was wrong because it has placed one of my photos into the folder of my brother, or vice versa. But this is not that surprising because we look alike, right? So even for some people in the street will tell you, oh, you look very much alike, or you look more and more alike. So that's why, of course, this kind of classification strategies based on attention plus feed forward will not succeed 100%, but will still be very useful, because out of the thousands of photos that you might have in the computer, you will get most of the work done without any effort from your side. Okay, so but this is about managing data, representing data, classifying data. This can be used also for generalization, of course, in order to identify who are the other persons appearing in that picture. But this lacks the generation capacity that probably is the most, say, surprising aspect of modern artificial intelligence. So we can do, for instance, a test here. Let me see if I can open my chat, and then can you see the window of my chat?
Yeah,
and
we
then
can.
I say, okay, so can you write a poem about 40 scientists gathering online a dark night of October for a Zoom seminar of the Turing Institute. Okay. Okay, so I am asking ChatGPT to write a poem, and this is a question that I just invented now. I'm sure ChatGPT has never seen this question before, right? And then I asked ChatGPT to do it. It takes a while, right? Just a few seconds. And here you have the poem, okay? The night seminar. 40 faces flicker on the screen, squares of light in the October gloom. Outside the wind rehearses equations on the windows of silent rooms, right? And then the poem ends saying, and when leave meeting ends the ride, 40 minds fade into night, but somewhere in the hum of thought, the algorithm still burns bright. So I will send this poem to Boumediene.
Yeah, it's quite nice. Yeah, I think we should share it.
Yeah. So you see the capacity of these tools of generating are amazing. It's amazing, right? So how can we explain? So what I said until now, control, supervised learning, the theorem of universal approximation, density, training, gradient descent, attention. I mean, it's fine. We all know all this makes part of modern success of machine learning and artificial intelligence, but this is not sufficient, right? We are doing something else. Somehow, the same occurs in this web page of this person doesn't exist, in which every time you click, you generate a new picture of a person. You certainly know this page, right? So the name of the page is This Person Doesn't Exist, so it's very easy to recall. And then if you go there, and maybe this one, okay, whenever I click in This Person Doesn't Exist, I get a new face of a person that doesn't exist. Okay, every time you click, you get a face, man, woman, child, elderly, of a person that doesn't exist. None of this person exists. Okay, so what is this generative AI doing? And what are the mathematical foundations of this capacity of generating new images that for a human eye, it will be very hard to say they are fake, right? When I see them myself, at least, I cannot really say why this face of this lady doesn't really exist, right? Okay, so what is behind? So what are the mathematics of generative AI, or some of the mathematics of generative AI? And surprisingly, this is very much rooted in the classical, say, properties of the heat equation, right? So let me recall you. So the heat equation now, this looks like a PDE class, partial differential equations. In the bachelor diploma or in the master diploma, the PDE, the Gauss introduced, right? The same Gauss of the Gaussian, right? Or Gauss and Legendre for least square, the same Gauss introduced the heat equation. The Gaussian, the fundamental solution of the heat equation is the Gaussian, right? And we know that it's not only used in order to describe the propagation and diffusion of heat, it's very much a model appearing fundamentally in population dynamics, in social dynamics, also in biology, in many other contexts, in finances and so on, right? The diffusion of propagation in information theory. It's a linear model. It's very nice. It's a parabolic equation. There is a unique solution. The solution becomes very, very regular. You can decompose it in Fourier, and you see how the high frequency modes are damped. But, there is, of course, always a negative side, and it's the fact that because the heat equation is so much regularizing in the forward sense of time, in which, as indicated in the formula here below, you are convoluting the heat kernel with the initial datum to get the smooth, smoother shape generated by these dynamics. If you try to reverse the sense of time, you will never be able to do it, right? So the heat equation is the prototypical example as Tikhonov observed, and which led to Tikhonov regularization, something we use very much in inverse problems and in optimization problems to make, optimization processes more stable through coercivity. He observed you will never be able to, reverse the sense of time, right? Very much like in real life. We can evolve in a forward sense, but unfortunately not in the backward sense. There are estimates, though, for the backward heat equation that are very much nonlinear in the sense that the process being, say, non-reversible in the classical sense of time, right? So if you really want to get estimates, you have to take into consideration how complex the initial data you are considering is. So this is related to, to the frequency number. You can somehow, as explained here, give the reverse of the Poincare inequality adapted to every solution. And there is some way of, Karleman inequalities were also developed in order to deal with these ill-posed problems. But of course, the stability estimate will always be very weak. You have some kind of logarithmic backward stability for the heat equation. So in a different context, Li and Yao, St. Yao, in the 80s, they made the following fundamental observation. They said, well, as explained before, the heat equation is very much ill-posed in the backward sense of time, but there are some universal bounds that, in particular, the non-negative solutions of the heat equation, like the Gaussian, fulfill. So if you give me any non-negative solution of the heat equation, this is what Li and Yao proved, in the Euclidean space of dimension n, right? And n, of course, in physical applications is 1, 2, 3. But when we are dealing with data, as we have explained before, we are dealing with images or videos of high resolution. The dimension capital N can be huge, right? In data science, regardless what the dimension capital N is, they said, if you have a non-negative solution, you have this inequality. The Laplacian of the log of u is greater than minus capital N over 2t. And this was the key observation we did in this joint work with Can Liu, who is a maître de conférence in Dijon, in France, right? In order to explain the success of modern methods of generative AI, right? Okay, so for PDE experts, this Li-Yao inequality is very much related to the semiconcavity of Hamilton-Jacobi equations, is related to the one-sided Lipschitz condition of the Barger's equation, and so on, but I will not enter into this. So now let me explain you why this inequality of Li and Yao, that was well known 40 years ago in, in the context of geometry when dealing with the heat process, why this inequality is relevant in nowadays generative AI, right? Let me explain you how, in a very simplistic manner, how people proceed. So assume I want to generate pictures of, experts in AI. So I take, we are 23 people now online. So I take these 23 pictures. Each of these pictures becomes a data set, which is representing part of this manifold of, the big, space or manifold of experts in AI or mathematicians working in AI, right? Out of these pictures, which are, specific locations in this high dimensional space, I build the empirical measure. It's just the combination of the Dirac deltas. With this combination of Dirac deltas, I solve the heat equation. This will lead to a combination of Gaussians. This is diffusing this information very much, in space-time. And once I get to the end, I try to solve the heat equation backwards, exploiting the fact that because the heat equation has some intrinsic instability, these intrinsic instabilities, oscillations of the backward heat equation will probably bring me to a different location which are those precisely of the new pictures I am willing to, to show you. Of course, I need this forward-backward process to still have a very strong mimicking capacity, because you still want to identify photos of individuals that look like data scientists. But of course, you also want to have some generative capacity, because you don't want to get to one of these 23 photos you already knew, right? So you want to generate new photos. You want to generate new poems. You want to generate new images, okay? So how does it work? Well, what people do in diffusion models for generative AI is very smart. They say, listen, I have to solve the heat equation backwards. This is ill-posed, but I can make this heat equation to become a Fokker-Planck equation by simply breaking minus Laplacian into Laplacian minus 2 times Laplacian. The minus 2 times Laplacian becomes the divergence of the gradient of u. The gradient of u, I can write it as u gradient u divided by u, and the gradient u divided by u is the gradient of the log of u. And now if I call the gradient of the log of u, I call the score function s, I see that the backward heat equation can be written as a Fokker-Planck equation, but now with the diffusion in the right sense of time, which is prepared in order to be well posed in the backward sense of time. So miracle, the heat equation that is ill-posed in the backward sense of time now miraculously becomes a Fokker-Planck equation that is prepared to be well posed in the backward sense of time. But when you try to see what do you need on the vector field score function S, which is the vector field of the transport term in this Fokker-Planck equation, what do you need in order to show that this Fokker-Planck equation is really well posed in the backward sense of time? You realize that what you need is a lower bound on the divergence. But what is the divergence of the gradient of the log of u? This is the Laplacian of the log of u, is precisely the inequality that Li and Yao provide. So you see how this classical inequality developed in the context of geometry for completely different purposes turns out to be the key element you need in order to show the stability of the forward-backward process of generative AI. And once you realize this, you say, well, the solution of the Fokker-Planck equation is just the density of probability corresponding to the realizations of the corresponding stochastic ODE driven by the vector field generated by the score function. And this is precisely what you see when you increase or diminish. So here, no noise. Here, you increase the diffusivity, more noise. You see how starting from any initial configuration, whenever you click, this person doesn't exist. What this web page is generating is a new trajectory that is bringing you very close to the manifold, here represented by this lemniscata. This is the manifold of human faces, right? And every time you click in the web page of this person doesn't exist, what the algorithm is doing, reproducing one of these stochastic trajectories underneath this Fokker-Planck equation driven by the score function, is generating a new trajectory that leads to a new image, which is close to the manifold of real human pictures, and therefore it looks like a human picture, but it's not. So it's a new synthetic image of a human. So this is where I wanted to finish. So we have, made a small promenade, involving classical control theory, dynamical systems, applications to animal and human behavior, the links with, classical cybernetics, the fundamental results by Kalman, the course of dimensionality of Bellman, how this is transmuted into the field of machine learning through supervised learning by employing, the more advanced architectures of neural differential equations and attention mechanisms, and very much based on these ideas of Kalman and, the Rubik cube in order to control simultaneously trajectory, the role of attention mechanism of simplifying big data sets through clustering, processes. And finally, the idea that, surprisingly for PDE persons as I, when you try to understand and explain why generative AI works so well, you encounter that actually the key is some of the fundamental properties of the heat equation that until now were considered, more a curiosity because, nobody was interested maybe in the heat equation in very high dimensions. But nowadays, this is precisely what you need. So this indicates, as usual, right, that mathematics has this very property of being, on one hand, very diverse, but on the other hand, exhibit this very curious topology according to which all the different fields are interconnected, building a unified, sole, unique discipline, and to which extent nowadays artificial intelligence and machine learning represents a great opportunity for mathematics, either to use what we know in classical applied math for explaining the success of machine learning and maybe also for developing new algorithms for machine learning, but also in order to develop the new mathematics that will be needed in order to really accompany this revolution of AI. And now I let you decide whether it is a bubble or whether it's a scientific and technological revolution that came to our civilization to stay. Thank you again, Boumediene, for the kind invitation.
Yeah, thank you very much. Thank you for the nice talk. And any questions or comments? Yeah, Regan, please go ahead and unmute. Yeah, thank you.
Yeah, sorry, I was looking how to unmute myself. Yeah. Thank you so much, Professor Enrique, for a nice talk. And I learned a lot about the Norbert Wien, who started this kind of theory.